You might ask, okay, what would it mean for a sequence of random variables to converge? And we have already learned that there was this almost sure convergence. There was the convergence in probability, but there was a limitation there in both of these concepts. The problem was that we had to be able to define all the random variables and also the limit on the same probability space omega. And that can sometimes be a problem. If you want to do kind of analyze let's say, probabilistic models of different sizes, and you want to kind of find universal laws where the kind of size is not anymore feature of the model. So in that case, actually, you don't want actually these to be random variables on a common space. Or you might not care about how these random variables look as functions. Usually what we only care is the distribution of the random variable. So how is the law of xn behaving? And then we would actually ask, okay, does it converge to some other law? So this is maybe the question that we might like to study. And then the limiting probability measure, it could be a probability measure of some random variable, but actually it might be the normal distribution, for example. So actually there's maybe no natural random variable that we could associate here. So we might actually like to delete this and instead write here just some limiting probability measure mu. But if mu is a limiting probability measure, for example, the normal distribution, or maybe it could be the Poisson distribution, as we have seen in stochastic processes courses that in certain cases the Poisson distribution is a limit of some relevant things. So in that case, it's actually, if this is a probability measure, so, well, that's a probability measure as well. So it might be actually fair to write it this way. So what would this mean? What would be a kind of good way to characterize the convergence of a sequence of probability measures? So all here, mu n and mu, they are probability measures on the real line. And statisticians would call them distributions on the real line. Yeah. Okay. So how to define this? There are actually many answers. So one way is to think that, okay, maybe the probability of some event B, maybe these probabilities should converge for some B, for a class of B, or maybe for all B. For every Borel set B, maybe these should converge. This is actually one approach that you think that, okay, you define that, okay, the measures of certain sets should converge. And there's one definition called the total variation convergence. That means that there's a total variation convergence, means that by definition, it means that if you look at the difference, how much mass this measure gives to any Borel set B, and you compare this, you take the absolute value and you look at uniformly over all sets B, which are Borel sets. If uniformly you have this thing converging to zero, so then you call this concept as the total variation convergence. This is an extremely strong form of convergence for probability measures, and but it's very useful in let's say it's very useful in discrete stochastics. So if you study discrete models on countable spaces of finite, so then that's what you might use quite often. But for let's say Gaussian distributions, that's not good. The other approach would be actually to kind of leave don't focus on sets. Like you don't want to ask the probability of every set, and you don't want maybe to require all sets to converge. Instead, you might think that, okay, if I have a random variable, so what do I usually care about it? I might care about the expectation of the random variable for some, let's say, cost function. So I could think that in many practical models, this could be a cost function, or maybe it could be a reward if you like to maximize things. So it could be a reward, or in machine learning, it might be loss or risk. Or what else could be this be a performance measure if you do performance analysis like in queuing theory. or insurance theory, this would be risk. So actually, you might have a kind of your favorite measure function here that describes you what is important about this random variable. If this is what you do, so then for the convergence, you would like this this your favorite function of interest to be well approximated in the limit, and that's what you would like to do. So in the context of probability measures, this would be the integral of phi of x with mu n integrated over the real line, and you would like this to converge to the on the real line to the phi of x with this your limiting measure. And when we have these measures, so we can take this one away, and we remember that phi is some kind of a good test function or observable of interest. On the other hand, sometimes we don't know what precisely is the good test function, so we might like to require this for all phi in a class of functions. People in analysis would call them test functions. You might do the same if you like. So one key class is actually, we don't have time to go all of them, but a certain class corresponds to so-called the Wasserstein distance, and a certain class corresponds to so-called weak convergence. And that's what we will actually take as an example. So for all phi, which are functions from the real line to the real line, and which are bounded and continuous. So we require this to be true for every bounded and continuous test function phi, and we want these integrals to converge. If this is true, so then we define that mu n converges weakly to mu. This is the definition of weak convergence of measures, if this condition is valid. It's also called convergence in distribution. All right. Why is this so useful? Actually, it is useful because there's another wonderful theorem by Paul Levy. That's called Levy's continuity theorem. It says that actually Fourier transforms very nicely characterize this weak convergence of probability measures. Namely, Levy's continuity theorem says that there's a weak convergence of these probability measures if and only if the Fourier transform at theta converges to the Fourier transform at theta for all n, for all theta. So from the Fourier point of view, weak convergence of measures of probability measures is just pointwise convergence of the Fourier transforms. We don't prove this theorem here. The proofs are in the lecture notes if you like to read, but maybe it's not crucial for now. But that theorem, knowing the second kind of key theorem from Levy is here. Maybe you have a question here in mind?
Does the Fourier transform converge to the Fourier transform of theta, or if you see the notation here at the bottom, the right-hand side?
Yes, of course. Yes, of course. Yes. I forgot my hat.